Today we'll look at elastic collision in 2D. 2D means two dimensions. To refresh our memory, we've discussed collision, and we said that collision is of two kinds. One, elastic collision, and two, inelastic collision. Elastic collision is a type of collision where both momentum and kinetic energy are conserved after the impact. Whereas the case of inelastic collision is a collision where only momentum is conserved after the impact. But we've looked at it in terms of moving in the same axis. Here we want to look at it, what if it moves in the two dimension, both the x and the y axis. So let's look at this scenario. You have two bodies with mass m1, initial velocity u1, and the other body is m2 with initial velocity u20. It means that this body is stationary, and that's the reason why the u2 is 0. So after striking the object or hitting the object, it will no longer move on the same only one x-axis. It will be inclined at an angle called θ1. And in physics, we know that when we are resolving on the x-axis, we make reference to cos theta, and when we are resolving on the y-axis, we make reference to sin theta. But I want us to refresh our memory. Some will be asking, why cos theta, why sin theta? So assuming we have this is the angle θ1, and this is m1. This is our x, this is our y. So we can resolve this both on the x-axis and on the y-axis. So on the x component, we normally make use of this SOHCAHTOA. Sine means opposite of a hypotenuse. Cosine means adjacent of a hypotenuse, and tan means opposite of adjacent. So considering this is a right angle triangle, this is our adjacent, this is the hypotenuse. So we're talking about cosine. So we can say that cos θ1 is equal to adjacent, which is x, all over hypotenuse m1. So we can say that if we want to make x the subject, x now will be equal to m1 cos θ1. That is, we'll now resolve this on the x component. So if you want to resolve this on the y component, so we will now consider this angle. These are alternate angles. We still have the hypotenuse m1, and the opposite is the y axis, which is y. So in this case, you have opposite of a hypotenuse. That is, we can now say that sine θ1 is equal to y all over m1. So if you make y the subject, y will now be equal to m1 sine θ1. So resolving on the x components, we have m1 cos θ1. Resolving on the y component, we have m1 sine θ1. So let's apply the principles of conservation of linear momentum here. We know that for this, we can write this as m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. This is a case of an elastic collision. But for this case, M2 is stationary. So the whole of this becomes 0 because U2 is 0. So we can now write this as M1 U1 equal to M1 V1 plus M2 V2. So we can now write this into both the x components and the y components. So for the x component, we can write this as M1 U1x equal to M1 V1x plus M2 V2x. This is the x axis. Then for the y-axis, we can write this as M1 U1y equal to M1 V1y plus M2 V2y. This is the y-axis. So in terms of the angle, we can now integrate this into what we have just written in terms of x-axis and the y-axis. So for the x component, we can write this as M1 U1 cos 0. Because for M1 is still moving on a straight line, there's no angle that is involved here. So in that case, we talk about cos 0 equal to M1 U1, sorry, V1 rather, cos theta 1, because here we're talking about angle is involved, plus M2 V2 cos theta 1. But of course, we know that cos theta is 1. Cos 0 being, cos 0 is 1, so we can write this as M1 U1 equal to M1 V1 cos theta 1 plus M2 V2 cos theta 1, because cos 0 is 1. So we'll now have this. Then for the y component, we also integrate this and we'll have M1 U1 sine 0, because no angle is involved, equal to M1 V1 sine theta 1 plus M2 V2 sine theta 1. And remember, sine 0 is 0, so the whole of this becomes 0. So we'll have 0 equal to M1 V1 sine theta 1 plus M2 V2 sine theta 1. So in the next class, we'll look at how we can solve the practical problem.